So welcome to this pre-recording of the second review for the second midterm exam. So in the first 10 minutes or so, I will give an overview of the protocol, how the second midterm exam will happen, and I will also then give a brief overview of the material that is covered for the second midterm exam. Okay, so here is the important day, Wednesday 27 July from noon till 1:40. So this is an online course and one can follow this course asynchronously, therefore these recordings, but the exams must be taken at the same time for everybody. So the exams are happening online. There will be multiple versions of the exam. Okay, so the day of the exam is an important day, but I will email questions to you only if you signed up for the exam. So, and I will need to know this before noon on Tuesday, 26 July. So 24 hours before the exam, you must commit to taking the exam. So the exam is happening online, very much like you do the quiz, except that you will be emailed the questions. You will receive the questions in the PDF file, but also in a Jupyter notebook that you then may use to solve the exam. So there is the skipping policy, and I will get to that right away in the next slide. But here is the important protocol for the exam. So there is the signing up. So by default, if you do not do anything, then I'm assuming that you skip the exam, so that's an automatic process. If you skip a midterm exam, then your points are not lost. So if you skip the first midterm exam, the final is going to count for 300 instead of 200. If you skip also the second midterm exam, then the final exam will count for 400 points. So skipping the exam will simply mean that you do not do anything. Although there are other activities that you can do for this course, like working on the third project. So it may very well also be that this course has gotten at a very fast pace. So this is the 8-week summer. Normally we have 15 weeks in a regular semester, so this goes about twice as fast. So, and we have covered almost everything that is important in this course. So there are still about 2 weeks to get ready for the final exam. So there might be good reasons for skipping this midterm exam. All right, so one reason could be that you are completely overwhelmed with the topics. If this is the case after these 2 slides, then that is fine. So don't worry, there are still 2 weeks to catch up. So, what are the topics? So the midterm exam covers the chapters 3 and 4. Chapter 3 was called Calculus. So here I have expanded this out into functions, differentiation, integration, and series. You see the last 2 bullet points are special topics in symbolic numeric computing. So the solving of the constraint optimization made the transition to the next part. The symbolic numeric factorization essentially also gets back to the second part in the course. So what is important here, sometimes, so SageMath is based on Python, but sometimes you must know when to use SageMath functions when you want to differentiate and integrate. Sometimes you may want to know when to use Python functions. That is to prevent premature evaluation. So especially with arrays of symbols, that is important. So the third bullet point here, we have seen how to define functions, how to compute with functions to compute expressions. So I should say that there will be a list of review problems that I will present in the second part in this course. Please review also the quizzes, so that makes for 4 good problems. Also review the homework. So there is then a programming topic, memoization. Recursion is extremely powerful. One can powerful problem-solving technique. So one can go from one formula into a program that, if you're not careful, will be extremely inefficient. With memoization, we can store the results of the function calls. If what you are computing is linear in the dimension, then you often trade in an exponential number of function calls for a linear number of function calls. So then there are 2 classical calculus problems that we have seen. The slope of the tangent line at a point on a curve. One can compute this in 2 ways, either via implicit differentiation or via a Taylor series approximation. So we compute expressions that approximate other expressions. So in the first part of the course, we started with numbers approximating other numbers. For example, we've seen several rational approximations for pi. Here, actually, we're going to replace complicated functions by truncated series, which are polynomials. Another important topic is anti-differentiation or integration. So one can solve symbolically many integrals, provided that the symbolic antiderivative exists. If it doesn't, then we can still evaluate numerically the integral. Note that the hold is true is actually here very interesting for defining the integral. But be aware that even if you work numerically, that there are pitfalls, and in particular the singularities inside an interval. So this is the calculus part. Then we have the plotting and the solving. So here both parts cover as many lectures, 3.5 sessions, both. So both are actually equally important. Although in the fourth part, we actually go towards more the application area of symbolic computation and computer algebra systems. So it splits kind of halfway into the plotting, where we started with the 4 types of plots that in 2 dimensions. In 3 dimensions, we first started to distinguish between surfaces and curves. And both surfaces and curves, they may be defined explicit, implicit, parametric, and via polar coordinates. Animations are sequences of plots. We call them frames. And one can build a plot piece by piece, first computing the plots, and then before rendering them, one can add computed plots together. One can build very nice animations with this. So in a way, an animation is already an application of the 2 and 3 dimensional plotting. So then, in the last 4 lectures, we have seen how to solve polynomial equations. And actually, what is important in this course is the formulation of the problems. So if we solve problems in this course, we write them down in a normal form, which is which is typically a simpler representation. And then there are standard software packages that solve it. The second important aspect in this course is to interpret the solutions. And here is also where the plotting comes in. So the plotting is scientific visualization is a very important topic, but the plotting also is often extremely good to interpret the results of what we compute. Okay, I will end this slide part of the presentation of the review. Again, going back to my most important slide here, that is the action item. So before Tuesday, so this lecture happens on Monday. So within 24 hours of this review lecture, you will have to decide whether you commit to taking the exam or whether you will skip it. Okay, so let me now swap the slides for the Jupyter notebook. So I have 2 Jupyter notebooks prepared. So one notebook is with the questions. So this will be the form of the notebook as you will see the questions. So it will be question 1, question 2, and I can go through these questions very carefully. I will try to scroll through when I look at the answers, spending ample time at explaining, trying to understand what I'm after here. So let me briefly do this for questions one after the other. So I have 10 problems that are representative for the midterm exam. And actually what I have repeated throughout this course is that the single most important resource are the notebooks that you make. So the collection of notebooks that you make is the most single important resource. There are many notebooks that are posted during the course, but it's important that you yourself are able to solve the problems. So SageMath is based on Python, and list comprehensions are extremely useful, very one-liners to define the data where we work on. So the first exercise asks you to count the number of points with integer coordinates in a polyhedral region. In a way, this question is a great review question in that I hope that the polyhedra are still, the polygons are still somewhere fresh in your mind. So we've seen the convex hull problem. A related problem is to count the number of integer points inside a region. And one can solve this problem with list comprehensions, as I will demonstrate. The second question starts with a recursion. So we have a formula defined with base cases. So one can see that the single most parameter is the n, the controlling parameter that controls the recursion. So we have 2 base cases, 0 and 1, for which we have explicit answers. For all other cases, we apply the recursion. So the mathematical formula for this recursion has 1 parameter. In the SageMath function, I tell you the prototype. And here with recursion, on the slides I mentioned memoization. So if you are doing this just straightforward as a Python function, it has to be a Python function evaluated in the SageMath context, because the A and the B are left as symbols. So this is a symbolic computation. We will compute a weighted combination of the symbols A and B for some parameter t. Now, if one is not careful, this will result in an exponential number of function calls. So you will lose half of the points if you do not recognize that problem, and if you cannot provide a good solution for it. Okay, the third question is on defining a function, but now it's a mathematical definition. So we can view a function as, so we have an integral. The integral is the area, but now the area is on the interval 0 to t. So where t is actually the variable in the function that you're going to define. So as a SageMath function, one can take its derivative. So that's now the knowing when to use a SageMath function and when to use a Python function. So the previous question was a Python function. This question is a SageMath question. Taylor series. So one can define the Chebyshev polynomials via a recursion. So we have used that example to illustrate memoization. Chebyshev polynomials are so important is that they are already predefined in Sage. And here one can define the Taylor series, the Chebyshev polynomials as the coefficients of a Taylor series approximation for a generating function. And there is a difference between the two, but they are actually equivalent. Okay, question 5 should be something that you recognize from a former quiz. So it starts out by making a plot of a curve defined by an equation. I'm sorry, so this is, I'm misreading here. So this is question 6. So question 5 is the slope of the tangent line problem. Here as a review, I indicate both ways to do this. So that was actually question 5 was on a quiz, and there I was just asking compute the slope of the tangent line to the curve at a point. So that's the standard formulation for the slope problem. You can do this in a second time in two ways. Both of them are good. So in this review, I have a more elaborate question. I show how to do them both in the hope that you will remember one of them. Okay. Then that question 6 was also a question that you had on a recent quiz. So plotting equations, plotting curves by equations is often a lot harder. As we will see, one has to define the range, and then also one has to take care of singularities. So in a way, polar coordinates are often a way to get around the difficulties with plotting through singularities. Question 7 is a problem where one is asked to compute the number of extremal values, or the number of critical points of a function subject to a constraint. The constraint is here simply the unit circle. In the lecture we solved a more complicated three-dimensional problem where the constraint was a sphere. Set up this problem and then use a Gröbner basis to solve it. We started in the lectures doing question 8. We call this the Hilbert matrix. Here use this Hilbert matrix to solve a linear system. Questions 9 and 10 go back to our last session, so where we had the initial value problem from the differential equations, and then there is a polyhedral optimization problem. So these are the 10 problems which I now did in 10 minutes, which I briefly explained in 10 minutes. Now this lecture can get done now in less than 10 minutes because I can scroll through the solutions. Your exam will last 100 minutes and will have about 9 problems, so you will have about 10 minutes per problem. So in a way, going through this review that fast is extremely unrealistic and a little bit irresponsible of me, but there is the pause button. So you can use this recording wisely in the sense that you try the problem yourself and you wait for a hint. Okay, so I switched tab. So you see that I have now the same notebook, but because these are the answers, I have labeled the questions differently. So the first question is on list comprehensions, and here I also want to indicate something that we might have missed when we used our list comprehensions. You can have conditional if statements. So one can make double loops. So list comprehensions are the way to show the equivalence between lists and for loops. So there is an equivalence between data structures and control structures. A double for loop is a standard construction for tables and for tuples, for points. Then there are the one line. So what is actually not good is that I give the solution immediately in one code cell. So typically, if you would to solve this, please also start every exercise with a reset. So you can solve the questions in any order. All questions will have the same amount of points. They're all equally important. So start every question, every answer with a reset, so you don't have any baggage from previously solved variable names that you might have used. So here in particular, the x and the y, the I and the j, they are local variables. So they only exist inside the loop. Here we have the tuples that we take from the lists, and then we apply the filters. So there are other ways to do this. So you can define filters and work like this as well, but this is more the proper Python tree with conditional expressions. And the answer is then simply the number 230. So these are the number of points. Of course, you can also solve this with a double for loop, and within that double for loop the if style. So this is in a way also a programming exercise. All right, memoization then, starting with the reset. So what is the virtue of using memoization is that you recognize inside in the else statement here the original function, and here it's again not really irresponsible of me to show you immediately the answer. So in the lecture, so if you want to know how this is solved, we did this first without memoization. So you can build this up first without memoization, and then you check the base cases first. You first check for small values of n. The benefit of this way of working is that you can keep the logic of the control. There are 3 steps to do in a memoization. You add a dictionary as the last parameter that has a default value. The default value means that when the function is first called, there is this dictionary that is allocated. And the same dictionary is being used whenever the function runs. So that's the first modification. The second modification is that you check whether for the arguments in the function, so not a dictionary, but a for tuple in the arguments, that you check whether there is already computed. So the keys in this dictionary are the arguments of this function. If that is the case, then you simply look up. The other change is that you don't return. So you assign to the result. So the result and the return, they actually look a little bit familiar. But so there is the dictionary management. So if you compute a result, you have to store it before returning it. So there is quite a mechanic process of doing this. But you must have made at least one exercise to be comfortable with this. Alright, and indeed, the benefit is that SageMath can, without any trouble, compute large values. Okay, so then we have a calculus problem intertwined with a function definition and a derivative. So what is here a little bit strange is that the independent variable is the upper limit in the integration interval. So we integrate from 0 to t, and that is the independent variable. So again, the local variable is x. So I'm saying this here in computer science terms. This is also expressed in mathematics as the integral, where the most important variable is t in the function. The t then gets substituted by the number 1. So this is how the function is evaluated. We can compute the derivative, and you see here the benefit of defining mathematical functions within SageMath. So we can take the derivative of SageMath functions. We've seen, by the way, that you can evaluate Python functions as symbols. Then they become expressions. And then any expression can be turned into a SageMath. Know from the first part and the very beginning of the course, everything is typed. I did this I was quite disciplined with this, that whatever object that you have, ask for the type. And then you will see that when Sage complains that it doesn't want to do certain things, it's because you don't have the right type. Alright, Taylor series. So the Chebyshev polynomials can be defined via a generating function. So here you see the Taylor series expression up to order 10. From that Taylor series expression, I can select, so actually the Taylor series, if you use Taylor, they're actually represented as polynomials. So in a way, what is returned is an expression. It's an expression in t. So again, it's important, this is an expression in 2 variables, but we can do the Taylor series expression symbolically. So where the coefficients are essentially polynomials, so they are the Chebyshev polynomials. So that's the point of this exercise. And when one compares this, so it's often very good when you have a question that there might always be a conclusion. So even if you run into technical difficulties, you may want to type up what you understood from the question. So then I can still give you partial credit to see that you understood, but for some reason or another you made a type error. SageMath was not collaborating with you. Also for me, if you write a last sentence, then the grading will go for me much quicker. So there is typically a question that you need to answer in a markdown cell. Classical calculus question. It's also essentially a derivative, but the question is a little bit more convoluted. We have a curve, a point on a curve, and we can ask for the slope of the tangent line. What this means is that at that point, is the curve going down or up if we look into the direction of the tangent line. So the tangent line is a first order approximation. So that is the first way of solving it. We compute the Taylor expansion around the point of degree 1. And here you can immediately read off the slope as 1/2. So the answer is 1/2 here. So in the previous exercise I had the coefficient. Here you compute the coefficient with respect to x, the coefficient with respect to y, and you divide them by each other. Also flipping signs. So the slope is always interpreted as the function y equals m times x plus some intercept. Taylor series give you essentially the implicit form of the tangent line. Okay, so there is a other way to do this. So this other way looks more cumbersome, but it is a great exercise. It gives you immediately the slope function. It's great exercise because we get to practice everything that we did in the second part of the course. We define formal functions. We substitute. So here I substitute inside the function f, I substitute the new y, and you see that then I can take the derivative of the equation and solve for the derivative. Select the right hand side because solve always returns a list of equations except when we ask for the dictionary. Then comes the substitution. So this comes from the second part. We substitute being mindful of the order. So here I first substituted x and then I substituted for y at 1. So you can do it the other way around. But we are going to replace x by 1. So there is 1 and 1, but the 1 here is x, the second one is for y. So, and this is the y seen as function of x. When we compute the tangent line, we see the second variable in function of the first variable. And the slope indicates what happens with the second variable when the first variable gets incremented. Does the function go up or go down? Alright, so then we compare. So both approaches are indeed the same. So here I get the slope and then I make the tangent line. What you do when you compute the Taylor series, you get the tangent line and then you compute the slope. So look at the solution to the quiz which was posted. Then actually I get the slope out of the equation for the tangent line. Here the problem is solved differently. All right, plotting in polar coordinates. So here we have a nice implicit plot, and we motivated polar coordinates by difficult situation at the origin. Here, the origin is also special, but the implicit plot has no problems with this. Nevertheless, the transition to polar coordinates is a very interesting problem. Um, so it's not a problem here for the implicit plot because you see that the intersection at the origin is orthogonal, and apparently so there is a multiple point there, but the multiplicity has not really bothered the implicit plot. So we have a nice curve. We can factor this curve. So we've seen in the second part the algebraic factorizations. So also we return back to the symbolic numeric factorizations. Here actually what we do is we extend the factorization problem to two variables. So what we are going to do with this coordinate transformation, we're going to be able to pull out the pieces out of this curve. Um, how does this go? Well, we go over to variables r and t. We substitute the polar representation for x and y. We get an expression with sines and cosines. At this point here, one may simplify the trigonometric expression. Here I didn't do this because it looks small enough. And I mentioned earlier that the solve always gives a list of equations, except if you want a dictionary. So here I wanted the dictionary, and you see the factorization happening. But this is an interesting exercise. So typically, if we have periodic functions, we plot them between 0 and 2 pi, or minus pi and pi. But here you see now that there is a square root coming in. And if you try to do this, there will be a problem. So you can see that the cosine t times sine p times sine t crosses the origin multiple times. And this happens, so at pi over 2, the sine becomes 1. At pi over 2, the cosine is 0. So 3 pi over 2, we have something similar. At pi, the sine becomes 0. So it's important that this is also in some sense a root finding problem, which I solve geometrically here. The figure size is rather small, but once you look at this expression, you get to see the ranges. Oops, and here you see the ranges. So the solution is actually the plot, where I have factored this curve into two pieces, a green piece and a red piece, with the ranges. Okay, problem number 7. So this goes indeed fast if one has the solutions already done. But once again, please try to do this before really looking at the solutions. And also, there are still two versions, at least two versions posted of previous exams. Also, via the previous course websites, you may be able to find the solutions to those midterms. But again, try to practice on your own. And do this before the 24-hour window. So that is another reason why I have this protocol. This is an open book exam, but you must have the practice. You must have practiced something. All right, Lagrange optimization. Know that we compute the gradients. So this is another virtue of using SageMath functions. Otherwise, you use list comprehensions on expressions. That's fine as well, but you get immediately the expressions for the entire gradient. Note that here I'm using lambda with a capital L, and I'm adding also the constraint. So as a check, you must have as many equations as unknowns. So we have the two original variables x and y, and then I have the lambda, and I have the parameters a and b sitting in there. All right. This is a very interesting problem, by the way. What I was going to say is that this is a two-dimensional problem. On an exam, you may have a three-dimensional problem. So then don't forget the z. So figure out first what are the dimensions. Why is this an interesting problem? Because you have to normalize. So I'm asking now here to compute the normal form of this system, and that's a triangular form. And this can be done by computing a lexicographical Gröbner basis. But we have rational expressions. So this is where the normalization comes in. So if I'm asking for the numerator, then I will actually get the things that are on standard form. So here you see this first equation where we have dividing by a. If I'm asking for the numerator, then what happens is that one brings on the standard form. So in some sense, this is a great review problem because the material of the second part is still very important here. And okay, so as an exam question, perhaps as a difficult final exam, this could work, but I'm giving this here because this is also a great review already with looking at where normalization is important. Normalization of rational expressions. I can give you a lexicographical Gröbner basis and then ask how many solutions are there. Or the problem could start from problems in several variables, a system in several variables. So we have spent time in part 2 to convert to lexicographical coordinates. That would be the first half of the question. Take the expressions, convert them. That is also what is done here. So after the normalization, the normalized expressions are converted into the polynomial ring. And then there are these magical instructions. We formulate the ideal and we ask for the Gröbner basis. And then the lexicographical Gröbner basis is triangular. It's not so nice as we have done before because of these two parameters sitting in there. But there is a polynomial of degree 3 in lambda. So I'm staring at this now a little bit, and you can see that it is the last polynomial. Note that the parameters a and b are sitting in there. So it's at first sight it might be confusing. So I'm saying there is a polynomial of degree 3 in lambda. That's the last polynomial. So it might be good to actually point this out very explicitly. And then you have linear expressions. For example, the second polynomial is a linear expression in x. The third one is a linear expression in y. So you can solve, you can compute from here the expression. So I could say that the exercise should still continue here. Compute explicit formulas, so use this triangular form to compute explicit expressions for the coordinates x and y in function of the parameters a, b, and lambda. Alright, solving a linear system, if you ever have to do this, use the backslash. So that's actually the thing that I'm after here. We've had an extensive lecture on linear algebra with the matrix forms. I started out, the essence here is how you can solve systems rather quickly. So, and we define this as the Hilbert matrix. In numerical analysis, this is ill-conditioned. In symbolic computation, you have expressions. Well, so that is looks like a nice matrix. Except again, the problem with matrices in SageMath start from 0, not from 1. So here I give you the ranges. What is not okay, so there are several other problems that I can make from this, making any pattern. So we actually are making matrices from patterns, matrices from functions. It's not okay to type it in. I will only give you perhaps 2 out of 20, a kind of an effort, but that's really a pity. So you must use the proper formulas that we have seen. So these are matrices over the rational numbers. Sometimes I may ask, so this is the rationals here that you have to recognize. We have matrices over the integers, over the complex intervals, etc. Okay, I'm running a little bit over time. I have only 4 minutes left for the last 2 problems, and I hope that this might suffice given that the last session was on differential equations. So here we solve an initial value problem and the solution is plotted. Note that you can first solve it symbolically. It's a first order equation, so it will turn out to be rather simple, expressed with exponentials. Here is the function, and then there is the slope field, where we substitute in the right hand side the solution. So we are essentially plotting the right hand side of the ordinary differential equation. Alright, these are all the slopes, again a slope problem. So the last problem is a linear programming problem, where again it's very good to start with a reset. It's a maximization problem, except that it is not. So you see maximization, that flag is turned off. So it's important here that we recognize the standard form. So in the lectures we had a maximization problem. Here in the review we have a minimization problem. And by the way, I'm solving this in one of the ways. This was the first way, so that we have seen 2 other ways to solve this. If you solve this in another way, this is fine. So you can explicitly compute with the dictionaries, or you can also run the simplex method on this problem. So there are 2 alternative ways. Whatever you do, verify by printing, by showing. So that if you define it in the other ways, you have to convert to some standard form before you can look at it. So here, this is a confirmation of the constraints. So you have 2 variables. I will not go over them, but you can recognize that this is now a minimization problem. Then the remainder of this exercise, so actually is then solving it, and write a conclusion. Write the last sentence where you show that you have correctly interpreted the output. So this is a course where we formulate problems and we interpret problems, especially in this last part of the course. Okay, so I could go through these 10 problems. In a way, watching this review might give you some confidence, but please solve some problems, make some more homework, or do homework, look at the quizzes, make sure that you understand where things went wrong on your quizzes, and practice. So that's the main thing that I can recommend.